hopefully I am recording this. I had a student ask if I could. So if this works, I will post the recording from today to Brightspace. If it doesn't work, I won't. But hopefully, fingers crossed, it will. So we're talking about deserts, and one of the big differences between deserts and every other type of area we're going to talk about, or we have talked about with erosion, is that deserts don't have much water. So water can't possibly be your big weathering force or your big erosion force because it's just not really there. When there are large rainstorms, they will have a huge impact on weathering processes. But for the most part, wind is going to be your main erosion force, and weathering is not going to work in the same way here that it does everywhere else. There's not much water vapor at all. There's very low humidity, and there's not much liquid water. So the majority of your weathering processes require the presence of water. Mechanical weathering does happen. Rocks will break up into fragments over time, but even then, they're not going to be altered much, and they may not move much. So you have a lot of fragments of rocks that are directly sitting on top of their parent rocks. They're not moving anywhere. But there will be some chemical weathering that happens, but this is going to be a reduced chemical weathering because there's not water. And because there's not water, you don't have the organic acids either. And the organic acids are also low because there's reduced biodiversity here. Very few life forms as opposed to elsewhere in the world. But the types of weathering that occur are the formations of clay particles. So different types of clay will form as a breakdown product of your rock. You will get a thin soil that forms. It will be mainly air pocket and mineral particles. It won't have much water in it, and it will have very little organic matter. And there will be some oxidation of your metals and other metal-derived minerals that are in the soil that will occur here. Water is not going to have as big of a role, clearly. Your streams will be dry most of the times because there's not much rainfall. Does anyone remember how many inches a year we said was our cutoff for a desert? 10. Does anyone know when we met does anyone know what the average yearly total is for this area of the country of rain a year?
No, we hit it like a month ago.
Yeah, we hit it with 100 days left in the year. We hit it this year. It's about 40 inches, sometimes a little bit more than 40 inches. So we get 4 times as much rain or more than a desert area would. Desert streams are ephemeral. Do we know what that word ephemeral means? This means that they're there when there's water, but they're not going to be there all of the time. So when there's water present, there is a stream, and then frequently they will dry out. So they're only going to flow during periods of rainfall. And when they do, they have flash floods. Has anyone ever lived out west or visited out west and seen the flash flooding occurring? I may have mentioned, if I didn't, my dad's family all lives out in Tucson, Arizona. So we've gone out to visit, and there are signs everywhere where the road crosses what they call the washes. And the signs are like, do not cross if it's raining. And you're thinking, it can't possibly be that bad. But having been there when it's just a little bit of rain, and then suddenly it's the pouring rain, and everything starts filling with water, it's kind of surprising to think that in deserts they have flash flooding, but it occurs often. And it only takes 6 inches of standing water to move your car. Well, Frank's truck might take more than 6 inches of water to move, but for most of us, our cars can start floating in 6 inches of water. And in some of these places, their washes can be 2 to 3 feet deep that will fill with flowing water. If your car gets stuck in one, you're going to start moving with the water. And when they talk about flash floods there, it's very different from our flash flood. Ours usually take a couple hours to start having a flash flood incident. They can start having flash flooding in a half hour-ish of rain. Depending upon the area that you're in, they may call these ephemeral streams washes, arroyos, wadis, ganga, or nala. The wash is used in the United States. Anyone want to guess where arroyo is used? Mexico? How about wadi? Good guess, but actually it's used in the Middle East and Africa. Donga is for South America, and then Nala is used in India. So different areas have different historical names for these regions. And the reason that they tend to flash flood is that things don't drain well here. They have a very thin soil, and under that they have rock. There's nowhere for the water to go. And even though there's not much water here, most of your erosional work is still done by those flash flooding events, because otherwise the only thing that's left to move things is wind. This is showing you a flash flooding event. So you can see the idea of an ephemeral stream that in that picture is still a little bit, it actually looks like a little bit of water there. But usually those stream beds will be dry. And then when it starts to rain, you suddenly get this pouring effect. Is that a little bit better with the screen? We are actually gonna skip this idea and this one and this. We're gonna move on to the idea of wind erosion. So this is gonna work very differently than water-based erosion. Because does wind carry things well? Lots of wind maybe, but we're not talking about like tornadoes moving through and moving things. We're talking about 10 mile an hour, 20 mile an hour, maybe 40 mile an hour winds. Are they gonna move very much? No. We don't usually see those moving soil here unless it's an area where there's no vegetation and it's dry soil. The wind is just gonna be transporting the loose debris from one location to another. And one of the things that we have in your temperate regions, your tropical regions, tend to be vegetation that are holding the soil in place. But in the desert, there's going to be vegetation areas and then areas with no vegetation. So the areas with no vegetation are going to see a higher rate of wind-borne erosion than those that have vegetation. The fine particles are going to be the ones that are generally picked up and moved. And the heavier ones may be rolled along the bottom by the wind, still calling that idea as a bed load as we did in the stream. But it's still going to be different from water because water has a pretty low density. So it has a smaller competence, the smaller particle size that it's capable of moving, and it's going to transport less. Also, water is not confined to a channel, so it can transport things in multiple directions over a large area. But it generally does not move very much. Wind-blown material is pretty insignificant compared to things moved by water and glaciers. The main process that we think about with wind erosion is deflation. This is when it is picking up the loose material and it's going to move the fine sediments a long distance but leave the larger ones going through saltation, so bouncing across the bedrock, but most of them are going to be left there. Sometimes it produces blowouts where you find a shallow depression. So it's going to create small dips in the surface of the ground. And it will also create something known as desert pavement. We'll look more at desert pavement formation, and I think it's 2 slides from now. But this is what you find is the main type of desert surface cover. And it is large pebbles, large sand grains, with not too much fine material there. The other type of erosion process that we have in deserts is sandblasting. When things are picked up, it's your clay and your sand fragments. Sand is not going to be moved very far, so it will actually not go far up into the water, into the air column, but it will be moved, and as it does, it may move across surfaces, abrading them like sandpaper would. So you can see that there are some rock structures in deserts where you can see it's been broken down by moving sand particles. What do you think happened here?
The area where the grass's roots were kind of attached to stable place, the other soil around it.
And that other soil went through what's called a blowout condition. But there's a massive difference then in the ability of plant roots to hold soil and the ability of wind to move soil. You will find areas in deserts that look similar to this. Blowouts can't happen where there's a lot of rooted vegetation. They can only happen where there is free sediment. This is our formation of a desert pavement situation. They tend to form usually by deflation, like we see in the top picture, where wind blows away all of your fine particles, leaving behind the large particles as the desert pavement structure. But it can also happen in a different way, where your weathered particles, large particles, are there first, and wind blows in fine grain materials that then settle out over time underneath your large materials as they fall between the cracks between them. So there are 2 ways that it can form. But once this is well developed, those large pebbles, the large gravel pieces on the top, actually keep wind-blown erosion from occurring because the wind can't pick them up and usually can't pick up the sand that's beneath them. So this is why this tends to be the type of ground cover you find in a lot of deserts. We're going to mention 2 different types of wind deposits. The first is loess, and the other is going to be sand dunes. These, the loess ones are deposits of wind-blown silt. Sometimes clay will be involved in this. And wind is really good at depositing materials someplace else. When we find structures like this, what we're finding are silt and clay particles that have been carried in suspension by wind and dropped someplace else. And when they're dropped, they form these extensive blankets of silt and clay that form over many, many years. Frequently, it's blown out over the ocean, but sometimes we find it blown out into areas in the interior continents. This structure here in China actually is made of wind-blown sediments that have been deposited here from someplace else. The primary sources of this silt material are deserts and glacial stratified drift. And along with creating new rock structures on continents, loess is well connected with fertilization of the ocean because there tend to be lots of iron and some other nutrients that are with this silt that actually then accumulates in the ocean and helps build up the phytoplankton community. But sand dunes are probably the one you think about when you think about wind-blown deposits. These are mounds and ridges of sand that form and are changed by the way the wind is blowing. Sand dunes are not going to be something that continue to stay in one location. They are going to be constantly moving as air moves them, but they have two big characteristic features overall. The first is the slip face. This is the leeward side of the dune. What does the word leeward mean? Is it a word we've heard before?
Is it the shaded side?
It's going to be the layer that's in the direction that your wind was blowing. So most of it will be on the shaded side. What we're seeing here, if the wind, wait a minute, which way is the wind moving here? The wind is moving this direction. Yes, because the wind is blowing this direction in that picture. You also have cross bedding. These are your sloping layers that occur in sand dunes. But we're going to look at types of sand dunes because that is far more interesting. You can see here the idea of cross bedding over years. What happens is that it can form into sedimentary rock. Because as the wind blows in one direction for a long period of time, you're going to get these stratified sand dunes, and then as it switches direction, they're going to move in the opposite way. So where you have winds that are frequently changing direction, cross-bedding occurs. There are 6 main types of sand dunes. Sand dunes assume a pattern that is consistent, and the factors that influence what forms are, not surprisingly, wind direction, wind velocity, the amount of vegetation present, and then the availability of sand. So wind direction and wind velocity, obviously that's going to influence it. Vegetation, we already know, can influence it. And then the availability of sand is your fourth structure or fourth factor that influences it. The Barcan ones are our first. They are crescent-shaped sand dunes. As you can see here, it does look similar to a crescent moon. And the tips point downwind. They occur in areas where there is not much sand, and they will move, but they move slower than some of your other sand dune types. Transverse dunes are long ridges that have troughs that are at right angles to the wind. And you can see that by looking at it. You have these ridges, and then between each ridge is a trough. This occurs in areas where wind is steady, there's lots of sand, and there's no vegetation to get in the way. The abarcanoid is going to form in between the barcan and the transverse structure. You have scalloped ridges of sand that are forming at a right angle to the wind. So this is going to occur in areas where there's intermediate amounts of sand to these two. Longitudinal are long ridges of sand where they're parallel to the wind direction. They can get very, very large. They are some of your largest sand dunes that you'll find. And they happen in areas where there's a pretty good supply of sand. Parabolic look like the barcan, but the tips point into the wind as opposed to away from the wind. These happen in areas where there is some level of vegetation that covers the sand. They're frequently found on coastal areas. But during storms, where there's strong winds, they can be blown out and completely have this sand dune type destroyed. During Hurricane Sandy, one of the things that happened with a lot of beach flooding was the destruction of these sand dunes. And then our last are the star dunes, which I regret to inform you are mostly found in the Sahara and the Arabian deserts and not found in the United States. But if you can travel to locate them, it would be a great thing to be able to do. They form these strange isolated hills of sand, and they look like multi-point stars. That's where they get the idea of a star dune from. They happen where your wind directions are variable, and you may have wind blowing from multiple directions even at once. That is the end of chapter 6. Which brings us to plate tectonics. Who has learned about plate tectonics before? Who has never heard of this topic? Okay, that's good. Everyone's heard of it. How would you describe it? Or better question maybe, what do you think we're going to be looking at in this chapter? So we're looking at the movement of plates and the results of that? Absolutely. The theory of plate tectonics deals with a comprehensive view of the processes that have shaped Earth's surface features. So this is going to be your movement of your plates mainly. But our surface features include our continents and our ocean basins. Plate tectonics is going to explain a lot about the next few chapters because our understanding of earthquakes, volcanoes, and mountain belts, which are your next 3 chapters, are directly related to plate tectonics. Once we understood plate tectonics, we can understand their formation and their controls a lot better. And for those of you more interested in the biological side of some of this, plate tectonics can explain plant and animal distributions, both now as well as in the past. Plate tectonics are why Australia and South America have marsupials. Alfred Wegener is our scientist mostly involved with this idea. He developed the concept of continental drift and first proposed his hypothesis in 1915. And he published it, and it was called The Origin of Continents and Oceans. In the past, it had been assumed that oceans and continents were in fixed positions. We later learned that they're capable of moving. How do we know this? Well, we can look at things like continental crust migrations, the changing surface of the world, how the mountains are different and how they formed, the spreading of oceans, changes in the sea floor. And his hypothesis was rejected by the majority of scientists for about 50 years because I don't really know a better way to say this than because most Western scientists were American or European, and they didn't like that his data did not include data from those regions. His study included mainly data from Africa, South America, and Australia, which were not seen and not well studied because scientists generally were influenced by some of the prevailing elite of the time, that these were not the areas that we were going and studying. So there was, if you want, some racism, some cultural ideas of what locations and who were better people than others that did influence some of the thoughts against this. But also, there was a lot of fear because the other scientists looking at this had not studied these other areas. So they couldn't enter into that discussion. Don't you have those conversations with other people where you know a lot about something and they just assume you're wrong because they know nothing about it? And the argument or the discussion never goes anywhere because they just like have insults? That's kind of how this went. But his hypothesis was confirmed following World War II, in part by technology developed for the war and the use of submarines during the war. By 1968, we had collected enough evidence for the theory of plate tectonics to be a theory and not a hypothesis anymore. So it took 50 years of people basically saying you have no idea what you're talking about, and then about 3 years to generate all of the data to make this into a theory. His hypothesis dealt with the idea that there was a supercontinent called Pangaea that broke apart about 200 million years ago. Continents have since drifted into their present positions, and as they do this, they break through the crust. Now, not all parts of his hypothesis were really correct, and that's some of the other things we're going to see as we go through this. This is our modern reconstruction of Pangaea at the top, and this is his drawing from 1912 of what he thought the continents looked like when they fit together. Pretty similar? And to have not had the evidence that proved his hypothesis when he developed this idea, it's really amazing. He based a lot of his original thoughts on the fit between South America and Africa. Some of his first evidence comes from the fit of these two continents. When you look at them, do they look like they should fit together? The shapes? Absolutely. But it's not just a fit there. They do have a very similar coastline. The opponents to his theory said that coastal processes changed the coastline so they wouldn't fit. But when you look at the edge of the continental plate, which is beneath the ocean, they actually discovered it's a pretty good fit between these two structures. It's the seaward side of the continental shelf that matches. This was proven in 1960 by Bullard when he mapped the continental edges at a depth of 900 meters. But what he based a lot of other ideas on were the fact that there are identical fossils in South America and Africa. How could you have the same exact animals on South America and Africa in the past if there wasn't some type of connection between the two continents? It was based on two different types of fossils. Mesosaurus and Lystrosaurus are our two animal fossils, and then Glossopteris, which is a plant. If you look, you can see where these fossils were found. And the Mesosaurus was found between South America and Africa. It is a small, yes, aquatic, but freshwater aquatic, so it couldn't have swum across the ocean, reptile. It lived about 260 million years ago. And if it had been capable of swimming and the continents hadn't moved, wouldn't you expect that instead of going from South America to Africa, it might have gone to North America or Central America instead? Much shorter distance? Or what kept it from hitting Africa and not moving up to Europe? That was part of the thing the scientists were trying to think about, is why would it just be in these regions? Lystrosaurus is a large lizard, lived about 250 million years ago, can be found between Antarctica, India, and South Africa. About the size of a pig, and it built nesting burrows that have also been discovered along with fossils. Well, Antarctica is pretty far from everywhere, so unless at some point in time it was connected to the other ones, it doesn't make sense that it would be there. And India, Africa, and Antarctica, different climates, they had to be connected somehow. But the big one for a lot of people that made sense of all of these continents here being connected at one point in time was Glossopteris, a fossil seed fern, whose seeds have been fossilized and they were too large for wind-blown dispersal. How in the world could a plant be found in Africa, Australia, India, South America, and Antarctica, unless at some point in time those continents had been connected? During the 1800s and the early 1900s, there was a lot of exploration of the world by European scientists, bringing back fossil evidence from all over the world, trying to make sense of concepts like evolution and geology. Now, the other thing is that Glossopteris, like its, as we can find today, closest relatives, was likely a cool climate plant. India and Africa, and for that matter, South America, are they cool climate continents for the most part? No. So this indicates that not only were these continents together, but they weren't in where they're found today. They were someplace else in the globe, closer to a pole. But there have been other theories proposed for how things moved. This is from your textbook. I'm 90% positive. It's figure 7.5. The first is the idea that they were able to get onto logs and they were able to raft from one location to another. And it might be likely that a few individuals could do this. Plants likely could not, because that requires some active movement. But it also means they'd be able to find enough food and water to make an open ocean journey on a raft. The next are the idea of isthmian links. So these isthmus, these land links from one place to another, but we find no evidence of them. Another idea, and they aren't unicorns, even though it really looks like it in the shadowy figure there, is the idea of island stepping stones. That there were small islands that they were able to move between to get from continent to continent. Once again, there should be some geologic evidence for that. And then our last one is continental drift. And my favorite part of this picture is the dinosaur whose heart is breaking while his friend is drifting away from him. It's not quite that fast. So that part's a little bit misleading, that his heart is breaking as his friend is quickly moving away from him. It wouldn't quite be that fast. Which of these is most likely? As crazy as it sounds, is a continental drift. And there's some more evidence. He also matched rock types and different rock structures in some other continents. So he was able to picture how were other things together in Pangaea. There are rock structures that match between North America, Greenland, Europe, and Africa. And rocks that form in the same conditions are going to have similarities, aren't they? Similar magmatic components, similar crystal sizing. So we can match rocks from one place to another. These rocks were not the only place. There's also an igneous rock structure found in Brazil that matches that interior curve in Africa that's 2.2 billion years old. There are mountain belts that end on one coastline that continue the same type of mountain structure and formation onto the next. So the mountains, when they formed, were together. Matching geologic features and fossils is really helpful. It's kind of like putting a jigsaw puzzle together to figure out how this might have worked. Because if you have a jigsaw puzzle you're putting together, And you see pieces, you're looking for pieces that match, right? The first thing you look for is shape matching, but then how many of you then look and see, does the picture match? And that's what they're doing here. First is the shape of the continents, but then using the rock types or the fossil types as the picture matching to put together a jigsaw puzzle. He also used the idea of ancient climates. We had glacial evidence. And we also know where our coal swamps were and where oil has formed over time, which tells us a lot about the climates of what the forests were when those formed. There's a glacial period from about 300 million years ago over South America, South Africa, Australia, and India, indicated by lots of glacial erosion, glacial till, and structures like that. But if those continents are in their modern day locations, is it possible that we had glaciers in Central Africa? The climate would have had to be really different in Central Africa. But then we would expect to see glaciers going further up into South America because we'd expect their climate would have been the same all over the world. What makes more sense is when we move them down towards the South Pole. There are kind of two ways we can make sense of this. The first idea is a global cooling idea, but where the whole world could have been cold, and then this would have worked. But since our glacial ice and coal swamps occurred at the same time period, this doesn't work because coal swamps are indicative of hot climates, or at least warm climates. They won't form in cold climates. So it's not possible that the whole world was just cold. The other is this idea that everything had to move south or really far north in order for those continents to be cold. But the movement of South America, Africa, India, and Australia south, when you're looking at all of Pangaea, would rotate North America and Europe towards the equator, making them warmer, and it works. It would also work potentially if you turn the whole thing upside down. We don't think that's how it happened. So our main objections to Wegener's proposal were not just that all of the data came from places that our scientists hadn't studied. And at first, there wasn't a whole lot of criticism until his research. Oh, take a guess. What was Wegener's first language? German. The Germans were pretty much okay with what he had to say. But then his work was translated into English, French, Spanish, and Russian. And those scientists had a whole lot of objections. One of the big ones was when he was asked to provide a mechanism for how this worked. He said the continental crust breaks through the oceanic crust, and that's how it works. What do you think? Does that sound reasonable? No. One of the other ideas that was floated as an idea was gravitational forces of the moon and sun, which sounds good until you recognize that the tidal forces that strong would actually have halted the rotation of Earth. So that doesn't work. To have had gravitational forces strong enough to move the continents through the ocean would require the Earth to stop spinning because the moon and the sun would have almost equal gravitational pulls. Those of you who've taken astronomy, is that possible at all? And also, if the continents were cutting through, wouldn't you expect there'd be more deformation on the edges of the continents than what we find? So he had these kind of wrong ideas. He threw out this idea of tidal ideas and of the continents cutting through the crust. So because of that, a lot of scientists didn't catch on well, especially our North American scientists. But then as it becomes a theory, they start realizing he's not in fact wrong. The theory of plate tectonics is more than just continental drift. And that's kind of what helped to create it into a theory. After World War II, the US Office of Naval Research had to do something with all of their submarines. When we spend a lot of money on things like submarines, satellites, the government usually tasks the offices with then using the instruments they've developed to learn more about the planet. NASA has a big Earth directorate, or has at times had a big Earth directorate. We've developed so much technology for NASA. There's been a push by taxpayers and scientists to be able to use the technologies to better understand processes on Earth. It's why NASA funds a lot of research in astrobiology. And astrobiology can be done on Earth, and it studies in that hot springs and the bacterial communities found there, and the biological communities found on the bottom of the ocean at something that will be discovered through all of this, the mid-Atlantic, or the ridge systems where you have hydrothermal vents. But these submarines, we made a lot of submarines during World War II. What did we use them for then? Surprising the Germans, tracking the Germans, tracking the Japanese, and looking for other troop movements. They also, in turn, these other countries made a lot of submarines. Suddenly we had a lot of submarines that had tracking abilities and instrumentation on them. We started examining the bottom of the ocean floor. It took over 2 decades to get this information together to really start to make sense of it. Because the first thing that they discovered made no sense. There's a thin layer of soil usually. That one we understood. There shouldn't be much soil on the ocean floor. But the oldest rocks they were encountering on the bottom of the ocean floor were 180 million years old, which is a problem when the rocks on the continents are 4.5 billion years old, right? So your first thought, if you're one of those scientists, is likely there's a problem with my instruments, or I need another sample to run. But what we discovered is that's because the oceans are always being recycled. And ocean rocks are generally not going to be older than 200 million years old. But that was the result of this work. You know that we have the lithosphere, and the lithosphere is the crust in the upper mantle. It floats on the asthenosphere, which is your lower portion of the mantle. And crust consists of both continental and oceanic crusts. Hopefully you remember way back, I think it was in chapter 1, we talked about how those crusts are different. Your oceanic crust is thinner and it is denser. Your continental crust is thicker and it is less dense because they're made of different types of rock materials. So your continental crust is going to float higher than your oceanic crust. What are our 7 major continents? I say major because there's actually more continental plates than there are continents. What are our 7 continents? Someone name one. North America, South America, Asia, Africa, Europe, Australia, one more, Antarctica. India is its own plate. Madagascar is a fraction of somebody else's. There are some small plate structures. Some of them are not real plates. Some of them are portions of Pacific plates. Our largest plate is the Pacific plate, and it contains a lot of islands on it that are continent, that have continental crust structures to them. Many of our plates are beneath the ocean, but some plates you may have heard of include the Caribbean, the Nazca, the Philippine, Arabian, Cocos, Scotia, and perhaps one you hear people in California yell at sometimes, the Juan de Fuca. Have you heard of that one? That's what causes a lot of our earthquake movements in California. We'll talk more about that later. It's where you have two plates in California sliding past each other. And then there are some microplates that we won't probably mention. Much of our plates are beneath the ocean. You can see here where some of them are. So your plates generally contain both continental crust and oceanic crust. And we're going to look for a minute more at the asthenosphere. It exists beneath your lithosphere. It's hotter and weaker than the lithosphere. This is where your rock is actually capable of flowing. This is also where liquid magma is going to be produced. And it's going to be why continental drift can happen, because your plates are going to be moving across the surface of the asthenosphere. Which brings us to perhaps our biggest topic for this chapter. The three types of plate boundaries. You can see all different types of plates here. As these plates move, the distance between them is going to change a little bit. New York and Denver, are they on the same plate? So New York and Colorado, are they on the same plate? Both on the North American plate. Where would the UK be though? Which plate? Eurasian plate. Does it make sense that Colorado and New York would always be the same distance from each other because they're on the same plate? But the UK and New York could be at times different distances from each other because they're on different plates. There is a difference then. Things that are on the same plate are going to stay together. Things that are on different plates are going to rotate away from each other or move away from each other over time. If you look at this right now, you see blue, red, and green lines between the plates, don't you? Those are going to be our different types of plate boundaries. I should mention that there are times that things can be moving towards each other on the same plate. There are places in China right now that are moving closer together, but that has to deal with the movement of the Pacific plate and the shrinking of the Pacific Ocean more than anything else. Your three plate boundaries are divergent. And what do you think is happening to the plates at a divergent boundary? How are they moving? Away from each other. And we call these also constructive margins because this is where you're building new crust. So when plates are moving away from each other, new crust is forming. We also have convergent plates. What do you think happens there? They're coming together. Because they're coming together, these are usually called destructive boundaries because one plate is going to be changed in form or destroyed. And then we have transform plate boundaries. What do you think happens there? They're just sliding past each other. So there's no net loss or creation of crust at these areas. Divergent makes up about 40% of our boundaries. Convergent makes up another 40%. And transform makes up about 20% of our plate boundaries. So we're going to look at each of these in some more detail with examples. And then we're going to come back to these ideas for the next 3 chapters. By then, I think you will really know these ideas. I should also mention, I did post the review sheet for exam 2, which is in November. It's because we're going to do a lot of activities between now and exam 2. but I just posted it because I had time. Your divergent plate boundaries are your constructive margins. Your plates are moving apart, and as they move apart, the mantle is going to be able to upwell in this area. You're going to have magma coming up and forming new sea floor. It's going to create structures known as ocean ridges. The center of the ridge is actually called the spreading center, and this is where new sea floor is being created. What is going to happen is that the magma is going to come up through cracks and fissures there, and as it comes into contact with the very cold ocean water, it becomes rock. It forms what's called the global ridge system. The oceanic ridges form a structure 43,000 miles long, the largest structure on Earth. Starts in the mid-Atlantic, goes through the East Pacific, and then the mid-Indian Ridge. So we have it winding through, well, really 4 oceans at that point, because it's going to have to pass through the Southern Ocean around Antarctica to get there. But ocean ridges are not the only places where these spreading centers can form. They can also form on continents. When they form on continents, we call them rifts. You can see the Mid-Atlantic Ridge here, where there are the divergent plates, North American and Eurasian plate moving in opposite directions away from each other. There's going to be upwelling of the magma, and it is going to lead to the construction of new sea floor material. That means your oldest portions of the sea floor are going to be next to North America and Europe, as opposed towards in the center of the ocean. Seafloor spreading makes the mid-Atlantic grow about 2 inches a year. So we're getting 2 inches further away from Europe every year, on average. Not too fast. The fastest rate of plate movement is about 6 inches a year in the East Pacific. What do you think happens when this happens on land, though? Imagine your property grows by 2 inches a year. Sounds great. Oh, it's not moving. Provided, you don't have a structure built on it. You have a spreading center on a continent, it's going to form a structure called a rift valley. It may eventually split a landmass into 2 pieces. This is rifting occurring in Iceland. And what happens with rifting is you're going to get uplifting of some areas, but subsidence of others. I worry very much for the structures in that subsiding block, because over time they will have, their foundations are likely already cracked, but they're going to have severe structural problems with those buildings, because subsiding structure is going to be sinking into the ground, but generally it's going to sink a little bit unevenly. Rifting on continents happens when plate motions are kind of pulling your continent apart. But instead of it being pulled apart, it's getting thinner and weaker. And the mantle is going to upwell to try and fix that. But as it does, it's going to make the ground surface really uneven. Do any of you have roads near you that over multiple years have gotten really bumpy that were not to begin with? This is almost a similar process to that in the summer they get warmer and they start to warp a little bit. That's similar to how the magma coming up from the asthenosphere is going to warp this continent due to the stretching of it. Over time, the warping and rifting of a continent can lead to the formation of a new ocean. First, it upwarps the continent, then it opens a rift, then the spreading makes the rift decrease in elevation, and the spreading center generates a new narrow sea, which eventually becomes an ocean. Do you think this is happening right now anywhere in the world? Okay. We're seeing this occur at the Red Sea. At the East African Rift Formation, the Red Sea is becoming larger. The Red Sea is now in a stage called a proto-ocean. Eventually, over a long period of time, it will form a new ocean. Not surprisingly, there's a lot of volcanic activity in this region right now. As plates are moving and magma is being able to come up from the asthenosphere, Mount Kenya and Mount Kilimanjaro have very recent volcanic activity. Eventually, the Red Sea will split through part of Africa, and we may end up with some islands forming as this rifts away. So the Red Sea could grow, and the Indian Ocean could eventually use the Red Sea as a passage up through the Mediterranean. But there's a little concern here. You can see that the Red Sea is a linear ocean, but do you see any political concerns with this being a spreading center with loss and growth of land in different ways? Is it strange to think of geology potentially influencing wars and other conflicts that may arise as this region of the world goes through structural changes? The good news is it's slow. Here we're talking fractions of an inch, but geologic processes can make unstable areas that are governmentally unstable more unstable. Our next plate boundary is our convergent plate boundary, which is your destructive margin. This is where your plates are colliding, and generally speaking, one of them is, or more, so one or both of them are going to be deformed. When the plates collide and you're looking at an oceanic plate and a continental plate colliding, your oceanic plate is going to subduct. It's going to go underneath your continental plate. It's going to form a structure called a trench, and it is going to recycle itself back into the mantle and the asthenosphere. This is because your continental plate floats higher, and when the two come together, the one that is more dense is going to sink underneath the other one. The trench is the location where this subduction is happening. The Mariana Trench and the Tonga trenches in the Pacific are locations where this is happening. When the crust sinks, it starts to melt at 60 meters in depth. And it's going to generate new magma that is going to go up and feed volcanic activity at the continental margin. When this happens on the ocean side, it will form volcanic islands. When it happens on the continental side, it forms volcanic mountains as opposed to islands. Mount Rainier, Mount Shasta, Mount St. Helens, Mount Hood, Silver Throne, Garibaldi, these are all mountains that have formed through magmatic activity due to an oceanic continental plate convergence. But these aren't the only ways that we can have a convergent boundary. You can have two continental plates coming together. And when they come together, that's what you see at the bottom here, you're going to form a mountain range where the one plate is going to kind of go over the other one, and the plates are going to become knit together. We call that structure between them then a suture, as they form together to form large mountain ranges. India is attached to Asia in this way. And sometimes you get two oceanic plates where one of them will subduct under the other, and the result is the formation then of volcanic island arcs. We're going to look at an example of, at least one example of each of these types. This is Mount Hood. We see here that your continental plate overrides the ocean plate, the oceanic plate subducting. And there is this volcanic arch, which we see as mountains, forming all across the top portion of the North American plate here. This gives you Mount Hood, Mount Rainier, St. Helens, all of those have volcanic activity. They are what we see as mountains, but they are actually volcanoes that are dormant. What about an oceanic convergence? The Aleutian Islands, the Mariana Islands, the Tonga Islands are the results of these. But so are island chains you're probably more familiar with. The Virgin Islands, Indonesia, Japan, the Alaskan Peninsula of islands are all the result of two oceanic plates coming together, one subducting under the other. As it partially melts, it creates a lot of magmatic activity, which rises up, erupts through the surface of the other, and creates volcanoes that create landform as they grow. We have our Aleutian Islands of the Alaskan Peninsula right here, forming as a result of two plates moving together. And actually, maybe more than two plates moving together here. I know it's probably really strange to think of two oceanic plates creating what we think of as continental crust, but it happens. And then we have our continental destructive margin. The two collide. Generally, one is going to move a little bit higher than the other. One is going to be usually a little bit more buoyant, a little less dense than the other. But both of them are going to end up folding and deforming and squishing together to create a mountain range. And as they do, since neither of them is really going to subduct well, the mountain range is just going to form straight up from them. Like what? Like the creation of the Himalayas. India very, very slowly crashed into Asia and created the Himalayan mountains. When these two, if you want, think of a continental convergence like a car accident. They come together and both end up crashing into each other. Here it's really India that's crashing into the other. And there's deformation. The crust buckles, it cracks, and it all warps upward. The crust has become shortened horizontally, but thickened vertically. The Alps, the Appalachians, the Urals all form this way. And the reason for me, as horrible as it is, that a car accident kind of makes sense in this is, if you've ever been in a car accident, sometimes your bumper goes from being like, oh, here's my nice bumper, to very short and very tall all at once. And that's kind of how these mountains form. Our transform ones, these are really easy. You're not making any crust. You're not destroying any crust. Your plates just slide past each other. These are either called transform plate boundaries or transform faults. In your spreading centers, in your mid-oceanic regions, there's usually a lot of transform cracks because your two plates aren't usually meeting like this. They're usually meeting in like a zigzag pattern. And between them, they have these fracture zones, which are linear breaks. But they actually help in the aid of movement and construction of the new oceanic crust. So what does this look like when we zoom out from this picture? It looks like this. So there's lots of little breaks because the lines between the two plates aren't smooth. It's kind of a jagged edge. In the weaker locations, there will be some cracking that will become your transform faults. And these plates are going to slowly move past each other. There may be some friction as they do, but it was these ridges and these fractures here that actually helped us understand, in mapping the seafloor, how all of this worked. When we found that this structure wasn't just found in the Mid-Atlantic Ridge, but followed the whole oceans around the world, we realized, wait a minute, maybe Wagner was right. Maybe things are moving and this is how. But not all transform faults are as nice as those. Here we have our Juan de Fuca and our North American plate, and the Pacific plate. They're all moving in slightly different directions at slightly different speeds. The Mencendino fault is in the ocean, but it is related to the formation of the San Andreas fault and the Alpine fault, which is in New Zealand. Do you see how the San Andreas fault has Los Angeles on one side and the rest of California on the other? How many of you have heard at some point there's going to be an earthquake that puts Los Angeles into the ocean? This is why. Along that fault line, there could eventually be a split. If San Andreas movement continues, part of Western California will have a fault zone that separates it from the rest. The Baja Peninsula and all of that will eventually become an island. Maybe. Eventually. This doesn't mean Los Angeles will be safe. I like having the idea it's like, it's just going to be okay. The two continents are going to separate. Everything's going to be fine. There's just going to be an ocean in between them. There's going to be a lot of destruction if that happens. The earthquakes that occur here are the plates trying to let off that friction that they're building up. And there's going to be a lot more earthquake activity before it just kind of falls off and develops into an island of California. The fault, though, you can see when you look at the geology of this area. We'll look more at this when we talk about earthquakes. And all of this brings us back to Pangea. Your plates and your boundaries are migrating. You're destroying and creating new areas. But the breakup of Pangea occurred about 180 million years ago. When it broke up, we got a brand new ocean, the Atlantic Ocean. The way that it broke up first was a split between North America and Africa. What followed was the split of South Africa from South America, Antarctica going off in its way, and India in a fourth way. Australia and Antarctica then separated. India moved up and hit Asia. Greenland broke off of Eurasia. And the Middle East and Baja California joined in with their larger continental plate groups. And a structure called the Tethys Sea closed. We're going to look at each of these, but this slide is going to be the most important for our activity next time. So here we have the pictures. We're going to go through each very quickly. The first thing that happens is North America and Africa are going to separate from each other. And you can see they have separated in this picture. Next is South America and Africa separate. India separates off. Antarctica and Australia start moving on their own. By 50 million years ago, most things are where we think of them being. But North America and South America are still separated. India is hanging off by itself. Eurasia looks really different. And Australia is not yet at its current location. 20 million years ago, India starts colliding to create the Himalayas, and Australia is still moving. We see North America and South America finally coming together. And at present day, this is where we are. Looks pretty good, right? This is the idea of where we could be 50 million years from now. North America is separating from South America. But notice, Australia is moving a lot, yes? Baja California, which you can't quite see, has split off from North America, and it's now part of Alaska. So this did not work well for Los Angeles. Australia is now at the equator. And then this could be about 250 million years ago from now. This is a prediction. We have no idea if this is going to happen. It will be a new supercontinent, but it will not be Pangea. Life will be really, really different than it is today. How do we know that any of this is real? Well, we've used evidence from ocean drilling. The deep sea drilling project ran from 1968 to 1983, and it drilled hundreds of holes into the ocean crust, looking for sediments as well as basaltic rock to date. And this is where we were able to find how old the ocean rocks were. It also allowed us to age the sediments by reconstructing the fossil assemblages of phytoplankton and other fossils that were found there. Radiometric dating does not work well for this because as you recycle rocks and you metamorphosize rocks, the dating is wrong. Also, basaltic rocks don't really date well. The thickness of the ocean floor sediments actually do work really well with equations developed for looking at seafloor spreading. And in 2003, the Integrated Ocean Drilling Program started. And I should point out both of these projects are funded by the oil companies, because by understanding how old the ocean crusts are, you can figure out where to dig for oil. This is looking at how that project works. I've worked on deep sea ocean drilling sediments from the Integrated Ocean Project from Antarctica. So if you want to talk about those at some point, we can. I did not get to go to Antarctica. The last thing that I'm going to try and cover really quickly are the idea of hotspots and mantle plumes. This is what forms your Hawaiian Islands and your other kind of chains of islands. The mantle material that's warm rises up through the asthenosphere, bringing magma up, and we call these mantle plumes, where they form into islands where it comes into contact with the oceanic crust we call hotspots. You can track their movement over times, and they create some things at depth, but they can also create islands, like our Hawaiian Islands. The youngest island in the Hawaii chain is 1 million years ago. Midway is the oldest at 27 million years ago, with Detroit Seamount, which is not really an island, at 80 million years of age. Paleomagnetism, let me see. We'll do paleomagnetism next time. It's 4 slides. We'll do that right before we start our activity.